connect the named connecting physics to systems with modular spin circuits. The authors are Kemal Selçuk, Saleh Buneyn, and et al. Why we need a spin circuit models? First, we need to understand this. With the rise of the AI and the stagnation of the Moore's law have accelerated the development of the specialized hardwares and new computing paradigms. In this context, fast tools to evaluate emerging materials and device concepts have become crucial. However, as transistors have become smaller and smaller, we are reaching physical and economic limits. What is the physical and economic limits? The physical limits are the when we build smaller when we build smaller transistors. Generally they are built with silicon. The quantum tunneling effects become major issue, especially in under 5 millimeters. And as the number of the transistor increases, the number of the transistors in the microchips are increases, the heat consumption and the heat production increases. So it's a issue for devices. And why we need a spin circuit? We say the Moore's law, the number of transistor on microchips double every year, is a slow at the uh, beginning of the 2014. What's the Moore's law? Moore's law describes the empirical regularity that number of transistor on integrated circuits double approximately every 2 years. And we need a models more specialized. The CMOS plus X one of them. CMOS on emerging devices, referred to here as X devices, leverage phenomena such as ferroelectricity, ferromagnetism, spin dynamics, and phase transformation. Today we will talk about spin dynamics. The key strength of the approach, CMOS approach, is not just about the modeling phenomena, but more about its ability to combine the devices to new circuits and structures, and it's like a plug and play model. Here you can see some different uh, X devices. And normally in spin circuit approach evolved out of a two-component model where the spins are aligned. And in this model, it's very relatively intuitive. If there is a two species of current. One is charge, and the other one is spin. The spin one is the difference of the up and down spins, whereas the current one is uh, the electrons number and the speeds given by. And but in the when quantum effects enter our model, and when this spins are not collinear, they are non-collinear, we need to use more complicated model. This is the four-component model with non-collinear components. One for charge, and we use one for 1 by 4 matrix, 1 by 4 matrix, and this is one for charge and three for spin. This four component we say non-collinear spins for, and however the model is not based on four species of electrons. Instead, it relies on two components with complex amplitudes. In this model, 1 0 represents the spin, and 0 1 represents minus s spin, while a superposition of 2 represents x spin. In this figure, you can see the up spin is modeled as a superposition of the right spin and left spin. So when it's polarized, and the one part is vanishes at the spin torque effects, and the other part is passed through the layer. It's a non-intuitive model, and in this model we define our wave function as a UV transpose, and we define our density matrix as a wave function times wave function Hermite. And in this model, the spin components are trace of Pauli spin matrices times density matrix. The Pauli spin three Pauli spin matrices for X, Y, and Z. And the charge component is the just trace of the P. Uh, Even such non-intuitive effects are accurately captured by the four-component model, whose components are given by 4 by 1 matrices, and they are related by 4 by 4 conductance matrices with voltages. Spin transport with four-component circuits. The two main ingredients in the spin circuit approach are transport and magnetism models, and they need to be solved self-consistently. Here we can see some transport models, elementary transport models. Later on we will model them to more complicated circuits, and here we have elemental magnetic models, and they are some physical structures from these elemental models. Why we need these elemental models? Because we need to use them to give input to our SPICE or high SPICE circuit simulators to simulate them. And the spin circuit approach presents combines diffusive and coherent spin conductors, focusing on coherence on small active regions. Extension to other degrees of freedom are also possible. Transport timescales are generally much faster than dynamics, and this allows a lumped circuit description. And each new magnetization configuration in the circuits, and we have to solve our transport models for each new magnetization dynamics. And here is the key point: is the fully phase coherent description of conductors is often unnecessary, because the spin conductors conserve spin in 2 by 2 Hermitian part of our density matrix. And here in the right below of the figure, we can see how our conductors matrix and our current four component current uh, voltage changes. And in normal electronic circuits, we also can use two-port formulation of spin conductance. But in our normal electron circuits without spin effects, the I1 plus I2 from Kirchhoff current law is equal to 0. So this term becomes a one-dimensional term. So normally we use one port formulation of spin conductance in normal electronic devices, but in uh, here the difference is I1 plus I2 is not equal 0 anymore, because some spin transport effects change our current. And here is, as you see, unlike charge currents, spin conductors may exhibit non-conservative of currents and non-reciprocity. And here we will solve the problem for reciprocal for G12 and G21. When our model is reciprocal, our spin conductor G12, G21 equal G0. And by this method, we can describe our shunt conductance 1 and shunt conductance 2 from two terminal, like G11 plus G0 and G22 plus G0. And we ground shunt conductance. We plug the terminal to the ground, so it is analogous to our normal microwave circuit or long transmission lines. And another important point is in our view, however, spin circuit formalism is much broader. Even though starting from microscopic theory may not always be necessary or possible, phenomenological four-component spin circuit models can still be obtained. And our first simple element is the ferromagnet normal metal interface. For many spintronic devices, ferromagnet normal metal interface plays a critical role in functioning of the device. Sorry. When ferromagnet points plus z direction, conductance matrix are given by like this, and the conductance matrix is given by they are obtaining from a scattering theory or non-equilibrium Green's functions. And here G0 is the interface conductance and P is the interface polarization, the real and imaginary coefficients of the spin mixing conductance respectively. Series conductance in here produce spin polarized currents in response to a charge potential, and the shunt conductance dissipate transverse spin currents, enabling the spin transfer torque mechanism. As we said earlier, we plug in the ground, so we apply normal Kirchhoff loop rules to, and they are suitable with our high space or space circuit simulators. And as you can see from the matrices in series, there is no x or y spin term, just they are charge and for polarized spin term. And in the shunt conductance, there is no charge or polarized spin term. They are just x and y terms. Uh, Naturally, in cases where transit behavior is being studied, conductance must be updated along the movement of the ferromagnetic magnetization vectors. And with this given rotation matrix, we can express our magnetization magnetization in spherical coordinates in any arbitrary direction. And in circuit simulators, we generally first obtain a fully parameterized rotated conductance that receives instantaneous magnetization directions for transistor simulator. In this schema, we can see the fact that I1 coming I1 is not equal to I internal, so there is some spin transfer torque effect. And in the ferromagnet normal interface consists a series and a shunt component that both depend on the orientation of the ferromagnet. Uh, Here, the transport and magnetization module. Here is an example spin wall built of two interfaces shown, as shown in here, and there is also magnetization module that we will see in soon. And here the spin circuit models are the spin circuit model from high space is aligned with our analytical results, and we calculate our analytical results from this non-uniform Green's function. Uh, and in here we put all SLLG magnetization dynamics in -1 direction, and we left to relax and average magnetization measured over. We measure the average magnetization over time, and spin circuit models gave results consistent with Fokker-Plant equation and the analytic equation, as we can see. And here the one more important part is the remarkably multiplying two conductance matrices instead of adding them in a series seems to capture the non-trivial magnetic tunnel junctions. For example, when we build a spin wall, we have to speak about the magnetic tunnel junction. The intuition behind this is the exponential decay of conductance across two tunneling interfaces in series. Equilibrium proportional to G1 and G2, which seems to generalize to matrix conductance. And the other key factor is channel spin orbit coupling. Aside from the ferromagnet normal metal interface, the transport conductance considers this paper are generally based on four components spin diffusion equations. As another example, how coherent quantum transport can be translated into spin circuits, we now explore channels with orbit coupling. And we consider a Hamiltonian for two-dimensional semiconductor with rush band that shows spin-orbit coupling terms. In this equation, H0 represents the kinetic energy for two-dimensional electron gas. Alpha and beta are strengths of the rush band thresholds spin-orbit coupling respectively. And here we have a Pauli spin matrices and we have a wave number in x and y direction. And this terms lead to spin momentum locking, where the effective magnetic field seen by the electron dependent on this momentum. And with this microscopic Hamiltonian, it's possible to derive the four-component two-terminal conductances necessary for two-port formulation using non-equilibrium Green's function. In this figure, we can see our angular momentum is the sum of our spin angular momentum and the uh, rotational angular momentum. This equation can be considered the spin generalization of one well-known Landauer formulation obtained from non-equilibrium Green's function, as we say. And for example, for one-dimensional ballistic conductor, as you can see in the right-hand side figure, in this case, the y wave function is zero because it's one-dimensional, and the conducting energy, the Hamiltonian, results in G11, G22 equals 2q square over h, where h times I, where g0 is 2q square over h, and minus g1 over g0 is given by this matrices. And we studied the transport models, so we can pass to the magnetization dynamics via Landau-Lifshitz-Gilbert equation. To simplify complex magnetization dynamics, we assume a monodomain magnet treating the entire material as a single magnetic domain. Because in large ferromagnets, in experiments typically contain many domains, and to get realistic dynamical behavior is very sophisticated. So we need to use sophisticated magnetic tools need to be used, and these tools solve the partial differential equations that are hard to combine with our spin circuit simulators. And our monoatomic domain approximation gets better as magnets are scaled down to the small dimensions. But more importantly, it allows magnetism and transport models in circuit simulations appropriate with our high space or space. And the SLLG equation, Landau-Lifshitz-Gilbert, stochastic Landau-Lifshitz-Gilbert equation is a two-dimensional ordinary differential equation, as you can see, where the magnetization evolves around the unit sphere, surface of the unit sphere. And also we have an effect of a thermal noise in the stochastic model. And the effect of the thermal noise is given by this formula. This is the very important part for our for building new devices. To solve this Landau-Lifshitz equation using power circuit simulators, the equation can be expressed in the form of coupled capacitors. Here, there's an example of them. There's a MTG model, the magnetic tunnel junction model, and there's a LLG part, and this part is of the magnetic tunnel junction model is for heat diffusion component. And natural antiferromagnets with spin circuits. In the study of the magnetization, In the study of the magnetization dynamics, the monodomain approximation is commonly assumed, simplifying the analysis by treating each domain as a uniformly magnetized. A question arises here. Can spin circuit models be constructed to incorporate coupled magnetization? And the answer is the yes. Authors answer this question by studying natural antiferromagnets. And here is the process for measurement the frequency of the uh, uh, antiferromagnets, measuring resonance frequency for antiferromagnets with circuit simulator tools. We apply a DC magnetic field along z-axis, and we apply the AC magnetic field applied perpendicular to the z-axis with sweeping frequency. And the frequency where the response is maximum is identified as the uh, resonance frequency at the applied DC field. And the exchange field between two magnets can be obtained from an energy model of the energy exchange equation. Here's volumes are volumes of the two coupled magnetic regions. MS is the saturation magnetization, and G exchange is the exchange coupling constant, which determines the strength of the exchange interaction between the spins M1 and M2 are the and M1 and M2 are the magnetization unit vectors along M1 and M2. And from this equation, it's possible to obtain resonance frequency formula dependent on the magnetic fields. Uh, Here in the figure A, we can see of antiferromagnets where two sublattices with opposing magnetizations. And in B it's the spin circuit model of the antiferromagnetic material with two antiferromagnet layers analyzed by two Landau-Lifshitz uh, stochastic Landau-Lifshitz Gilbert coupled with exchange interactions. And here see the experimental results. This experimental results, this circuit experiment, and for manganese fluid 2, manganese fluorescent 2. And in these the analytical results and the spin circuit, the results from we measure from our spin circuit models like H-space generally. And they are perfectly matched. They are nearly perfectly matched. And in this experiment, we observed that around 10 Tesla, the antiferromagnetic spins undergo significant transition. At lower magnetic fields, the spins are aligned antiparallel as shown in the figure. However, as the magnetic fields reach a critical strength, and we're in 10 Tesla in this case, spins enter the spin flop transition region, and where they develop a small MZ component. This means spins are no longer perfectly antiparallel, but begin to tilt slightly aligning with the magnetic field direction, and this causes the spins precise around the field axis. Engineering antiferromagnets with non-local spin valves. An example of the non-local spin valve setup is proposed coupling low barrier nanomagnets to create Heisenberg machine using spin circuit models. Earlier section, we see how magnets can be modeled by coupling transport model with magnetization dynamics through the LLG equation. For a non-local spin valve channel materials, the authors introduced the normal metal model which describes the spin diffusion channels without spin orbit coupling, and represented by the P network with two shunt conductance separated by a series conductance. And these matrices are obtained from microscopic spin diffusion equations. Here in figure 1, we can see the Heisenberg machine with programmable spin circuits. Here there are many of low barrier magnets and the spin neutral channels from the Heisenberg array where an external charge current is injected into the LBMs. So for each individual LBMs, we uh, we um, we inject the external charge current. And the models in the functions are transport models, SLLG models, and roll of 4 by 4 matrices, as we say earlier. And here is another similar scheme figure. We can see the spin neutral channels are described by a combination of series and shunt conductors, and they are grounded, where each conductors is 4 by 4 matrix, takes into consideration the interaction between charges and spins in the x and y directions. And the LLG module solves the stochastic LLG equation as a function of the received spin current and the thermal noise. And here is the non-local spin valve with low barrier nanomagnets. Uh, as we say earlier, the current is injected and is very similar to our previous figures. And here there is a figure of how magnetization dynamics of the uh, nanomagnets with respect to time we can see from here. And in figure B, there is a in figure B there is a function of the average uh, average uh, average angle between magnet 1 and magnet 2, average angle between their magnetization directions. And this is the function of the our injected IC current. The Heisenberg model with its complex interactions and 3D magnetization vectors presents challenges in finding equilibrium low energy states. This is this formula. It's challenging to find. But by engineering LBMs to sample from this model, we can optimize charge and spin current interactions with the spin circuit approach, enabling the control of magnetization vectors and antiferromagnet coupling through the injected charge current. And we came to the functional spin circuits with transistors. Stochastic magnetic tunnel junctions and CMOS components are combined to the model and characterize a probabilistic bit within the spin circuit framework. Traditional magnetic tunnel junction is use a fixed layer where the resistance correlates with the magnetization of a free layer. With the rise of probabilistic computing and the need for fast energy efficient scalable random number generators, SMTGAs have been designed without fixed layers. And the examples we considered so far have utilized spintronic building blocks with increasing sophistication without transistors. And here, where the transistors where the transistors takes role, and we will see the CMOS plus X systems, where X is the MTG. Here Here and in figure A, we can see a self-consistent magnet transport model combined with transistor to model a probabilistic bit. There is a two magnetization transport models, two SLLG solvers, and here is a double free layer. Here is there is a double free layer LBM. And we have a FET inverter and FET. When we combine this spin circuits for component current and voltage with ordinary circuits that only carry charge currents, we only attach the charge current terminals to each other. What we mean by saying this? The rest of the current is independent. The rest of the current is normally charge current, and this part of the circuit have a spin current. When we connect our spin systems to the uh, just charge current system, we it's just connect to the current charge current, and any other spin information can be ignored in the extended charge circuits. And what's the interesting here is the double free layer MTGS exhibits an interesting voltage independent resistance profile, as we can see in the figure here. The resistance of the our MTG is independent of the voltage. And this behavior is reproduced by the spin circuit model, where two symmetric layers receive spin currents with opposite signs. As we can see in the B, the current of the first layer and the current of the second layer are opposite each every time. So this behavior comes from this aspect. And in figure C, we graph the cosinus of the cosinus between m1 and m2 with respect to the time, and we see uh, very very random very random mm, we see a very random distribution. And there is a slightly anti-parallel tendency, and this is due to the dipolar coupling, which is not completely overcome by thermal fields. And in this figure, we there are experimental results. In this figure, the double free layer are constructed with different thicknesses elements. Don't don't show a voltage independent aspect, but in the double free layer constructed with same thickness material is showing as a voltage independent magnetic field aspects. And figure 6a and 6 shows until full input output characteristic of the probabilistic bit that's obtained from our full model. There's the characteristic of the bits. These simulations demonstrate the tunability of randomness at different bias voltages. An important point to this important point is that the tunability doesn't arise from spin transfer torque effects modulating the free layer magnetizations, but rather from the changing transistor conductance by an analog input. So we change the transistor conductance and the R randomness changes. So it's because it's not changing with spin transfer torque effects, because we construct it as a double free layer, and it's a voltage independent. And lastly, we study the hybrid systems SMTG plus CMOS for energy efficient uh, probabilistic bit networks. Before delving into the system, the spin circuit approach integrates magnetization dynamics, noise fields, and interface conductance in the circuit simulator, enabling accurate predictions and device level evaluations. Notably, it predicted key features of double free layer SMTGC, which is later experimentally confirmed that the spin circuits were correct. In here, we built a hybrid system with combining uh, true random number generator and probabilistic random number generator. And why we combine this two? And because The true random generator generates high quality randomness using physical process such as SMTG noise. And whereas pseudo random number generator is randomness are uh, lower quality. And our hybrid goal is to use SMTG based TRNG to improve randomness quality of PRNG systems, making them more robust and efficient. How does the hybrid system works? Here's the key point one is the uh, our SMTG produce a physical random telegraph noise, and our CMOS circuit produce physical run our CMOS circuit process the RTN using a PRNG and lookup table to create a tunable probabilistic output. Sorry, here we can see it. Our CMOS digital block have PRNG and tangent of H LUT, and energy efficient p-bit probabilistic bit networks with sigmoid. We see the energy efficient probabilistic bit behavior with sigmoid line, and here why we use buffer tree, because at SMTG voltage there were no there was a lot of fluctuations, and it wasn't uh, clocked, and by using buffer tree we clock this signal, and as we can see here the difference. And we use one SMTG to connect thousands of CMOS with these systems. And these systems represent an energy efficient and scalable p-bit probabilistic bit model, which has demonstrated significant potential in offering scalable solutions to complex previously interactable problems. In here, we can see the experimental model of this schema, this figure. And we say they are energy efficient and they are physically smaller than our normal transistors. Why? As you can see here, the transistor counts for high quality a random number generator is just 4 in magnetic tunnel junctions, whereas is around 7,000 and 11,000 are for Zoc0 PRNG and Zoc0 pi bit. And in means of energy consumption, the SMTG p bit nearly consumes uh, zero energy. It consumes very 2 fermijoule energy just. And single SMTG, as we said, can drive thousands of transistors in CMOS. To conclude, the spin circuit approach provides a versatile and grounded framework that bridges the microscopic dynamics of spintronic phenomena with the macroscopic design of advanced electronic systems, paving the way groundbreaking innovations in the beyond More era. And thank you for listening. It's the end of my presentation. Thank you for listening. Means end of my presentation.